So this video is meant to help with mole conversions and with PV equals nRT, the ideal gas law equation, which also involves mole conversions. So let's go ahead and do an example. So the first thing we're going to talk about here is mole conversions. So let's say I had a problem that said I have a 10-gram sample of oxygen, and they want to know how many moles of oxygen that would be. So the first thing we're always going to do is set up the molar mass of oxygen. So when I look on the periodic table, each oxygen can be rounded up to 16 grams per mole. So 32 grams of oxygen would be 1 mole. That means one huge grouping of oxygen weighs 32 grams. And it's so small, we need that huge grouping to make that number reasonable. Okay. And in this case, it says, well, what if you had 10 grams of O2? How many moles would that be? All right, so we're just going to cross multiply, in this case, by taking 32 times x and setting that equal to 10 times 1. So we're going to take 10 divided by 32 and get an answer, and that answer is going to be 0.31. And so this equals 0.31, but that's not the answer. The answer is 0.31 moles of O2. And that should make sense. There are 32 grams in one large grouping of moles. What if you only had 10 grams? Well, it's going to be less moles. All right. Let's go ahead and do another problem here. Let's say in this case now we have 0.025 moles of C3H8 gas, and we want to know how many grams that would be. Well, that's going to be the same thing again. What we're going to do is get the molar mass of C3H8. So that's going to be 12 C's. Well, each C is 12 multiplied by 3, so it's going to be 36, plus 8 hydrogens. I'm really downplaying this calculation here, which is 3 times 12 plus 1 times 8, which is going to be equal to 44, because I really don't think it's that big of a deal. I think you really can just look at the periodic table, get 3 carbons, add those up, get 8 hydrogens, add those up, and get a number, 44 grams per mole. Okay. So there are 44 grams of C3H8 in every 1 mole of C3H8. And in this case, I don't know how many grams I got, but I know I got 0.025 moles. So this number is going to be much less because I have a lot less than a mole. So 0.025 multiplied by 44 equals that divided by 1. But that's going to be equal to 1.1. That's not my answer. Grams of propane is my answer. Got it. Boop. All right. So now let's talk about the ideal gas law equation. So we know that for something to be ideal, number 1, it's got to be small. For something to be ideal, number 2, it's got to be nonpolar. This makes it light and really keeps it away from the other gases, limits the intermolecular forces. We know we want it to be at a high temp and a low pressure. We know that we want it to be elastic, and we know that we want it to be random in its motion. Well, there's a 6th one. It needs to be able to behave according to the ideal gas law equation, where pressure is measured in atmospheres, volume is measured in liters, N is moles, R is our ideal gas law constant, 0.0821 atmosphere, liter, mole, Kelvin, and T is our temperature in Kelvin. One common thing that's done in these kind of equations is that value there, N, is often given in grams, and we work in between that. Okay. So let's go ahead and let's look at a problem. Let's say that we had a pressure value of 1.3 atm, a volume value of 200 milliliters, a mole value of 1.32 moles, and they wanted temperature. Okay, so this would be written in an equation, though, or in some sort of statement. They'd say the pressure of a gas is 1.3 atmospheres, while the volume is 200 milliliters. The moles is 1.32, and the temperature is. And if they ask for the temperature in Kelvin and degrees Celsius, we need to know that the answer first comes out in Kelvin. So let's calculate this. PV equals nRT. T equals PV divided by nR. So P is 1.3. V is going to be 0.20 liters. N is going to be 1.32. And R is 0.0821. Now, a common mistake when you're doing this together, you got to treat that all as one thing and that all as one thing, or else you won't get the right answer. So let's do it. 1.3 times 0.2 divided by quantity 1.32 times 0.0821 n quantity equals 2.3. So 2.3 Kelvin, and I subtract 273, and that equals negative 270 degrees Celsius. Okay, let's do one last one. Let's say in this case they wanted pressure. Okay, we don't know pressure. We know that volume is 2.5 liters. We don't know the moles, but we were given, let's say, 22 grams of CO2, and the temperature is room temperature, 25 degrees Celsius. So let's go through and let's plug this in. We know that PV equals nRT. We know that P equals nRT divided by V. And we know that P equals N. Well, the first thing we got to do is we got to actually do a conversion here. We got to convert that to moles. Okay, well, let's go back and let's do a mole conversion. We know that there's 44 grams per every 1 mole of CO2. So 22 grams is how many moles? Well, we're going to solve for X, and we're going to get 0.5 for that. And we're going to get 0.0821 for that. And we're going to add 273 to that. And that's going to give us 298. And I sound really annoying, sorry. And we're going to divide it by V, which is 2.5 liters. We're going to plug all of that stuff in. So 0.5 times 0.0821 times 298, that, divided by 2.5 equals 4.9 atmospheres. Okay, so with all these problems, the trickiest thing is the mole piece. Remember that this is a skill that we've learned in the past.